Have you ever poured your heart into writing a solution, confident that your logic is absolutely flawless, only to hit a wall because your memory fails? It is one of the most frustrating feelings in competitive programming, when the math is correct, but the computer simply cannot handle the sheer size of the numbers. Hello everyone and welcome back. My name is Supratim and I am your coach here at Techmine Guru. Today we are going to fix that overflow problem once and for all. We are diving deep into DSA lecture 21, exploring the fascinating world of modular arithmetic and GCD. Our agenda for today is packed with powerful techniques. First, we will introduce the fundamentals of modular arithmetic. Second, we will tackle the challenge of mod on power, specifically calculating a to the power n mod m. Third, we will apply our skills to solve the count divisible pairs puzzle. And finally, we will break down GCD basics and properties. So let's get started. Imagine you are tasked with writing code to find a to the power n mod m. The constants are massive. A, n, n can all be up to 10 to the power 9. If you try a naive approach, you are looking at calculating 10 to the power 9 times 10 to the power 9 times 10 to the power 9, which spirals out of control into a massive 10 to the power 27. That is a guaranteed overflow. The solution to this isn't relying on bigger data types. It's about setting structural boundaries. Modulo, using the modulo boundary. So modulo protects your variables by wrapping infinite growth around a strict boundary, forcing numbers into a closed loop from 0 up to constant minus 1, which is in this case is b. So if a mod b is been done, that means your answer for a mod b will come in between the range of 0 to b minus 1. So now we will see some basic properties of modulo. So these are the 6 rules of the containment. First is the addition rule, where a plus b whole mod m can be expressed as a mod m plus b mod m and whole mod m. So this is pretty straightforward, right? Similarly, if you see for the multiplication also, it is similar. So if a multiplied b whole modulus m, this can be expressed as a modulus m multiplied by b modulus m and whole modulus m. Next, we will see what if we keep m here instead of b. So if you express this in these terms, it will be a modulus m, right, plus m modulus m, right, and finally whole modulus m, right, if we use our first formula. So any number when done modulus his own number, the answer will be always 0. So a plus m modulus m can be expressed as a modulus m only. And if you closely observe, a modulus applied on a number n number of times is equal to one time of doing it, right? Now we will see the subtraction, which is a minus b modulus m. So in this case, the result will be a modulus m minus b modulus m plus m and whole modulus m. So why plus m is added? We will see that in a while. Before that, let's understand the last property, which is a to the power b modulus m. So this can be expressed as a modulus m to the power b and then modulus of the complete result. So let's see one example for a plus b modulus m. Suppose a is given as 9, b is given as 8, and m is given as 5. And assume that your data type maximum limit is 10 only. So if you do 9 plus 8 modulus 5, so this 9 plus 8 will give you 17, right? So this 17 will overflow because your data type max limit is 10 only. So if we express it in this way, 9 modulus 5 and 8 modulus 5 using the first property, a modulus m plus b modulus m. So 9 modulus 5 will give us the result as 4. Similarly, 8 modulus 5 will give us result as 3. Now, if we add these two numbers, so this is under the data type range, right? So when we will do final modulus, 7 modulus 5, which will be 2. And also if you see in total also, that 17 modulus 5 will give the result as 2 only. So we can achieve this via this only. And similarly for the multiplication on. So if the data limit is 10, so then 9 modulus 8 will be expressed as 72, which is much larger than 10, right? So it will overflow. Instead of that, if we modulo this, it will come 4 into 3, which will be 12, right? And 12 modulus 5 will give the result as 2, right? And if you think like this also, that 9 into 8 will give the result as 72, and 72 modulus 5 will also give the result as 2 only. So the answer will not change. Now let's see why in a minus b modulus m, we get an extra m. So let's take an example that when a is equal to 13, b is equal to 4, and m is equal to 5. So if you simply apply the formula like addition, 13 modulus 5 will be 3, right? And 4 modulus 5 will be 4, right? So 3 minus 5 will be minus 1. So in some compilers like Python and Java, it will give the result as 4. But in C++, it will give result as -1, which is not correct. So for this, we just have to remember that we just need to use one extra plus n in the answer. Similarly, for the nested modulo, if you see, if you do 10 modulus 3, the result will come as 1. And if you keep on applying modulus on that same, the result will not change. And lastly, our last property, a to the power b modulus m, can be expressed as a modulus m power b and whole power m. So to understand this better, if you have given 37 to the power 103 minus 1 modulus 12, it will be a very big number, right? So we can apply this formula here. So 37 modulus 12 will give the result as 1, right? And whole power 103 will again give the result as 1 only. So 1 minus 1 will be 0. Now let's come back to the problem again. So if we have given 3 integers a, n and m, and you have to find a to the power n modulus m using recursion. So in our last lecture, we already learned about how to do a to the power n using fast exponential method, right? So if you see the constant, so it will definitely overflow, right? But if we use the power of the modulo, we can come out from this problem. So this code you have already seen in the last class. So if n is equal to 0, you have to return 1. This is the base condition. And then you have to keep this recursive function's value at p, and you have to do p into p modulus m. So here your answer will never cross the constant because you have applied modulo m here. Similarly, if the number is odd, then p into p into a was the result. So you can simply put modulo of p into p and then multiply it with a, and then you can finally take the complete modulo over the answer. So if you do this approach, even if the constants are bigger, your answer will never do a memory overflow. So let's see one problem. You have to count pairs I comma j where I is not equal to j, and also a of I plus a of j modulus of m should be equal to 0. So suppose you have been given an array 4, 3, 6, 3, 8, 12, and the m is 6 here, right? So if you see, if you add the 0th element and the 4th element, the pair sum will be 12. So 12 is divisible by 6. So this is one pair, right? Similarly, if you see first and the third number, which is 3, 3, so 3 plus 3 will be equal to 6, and 6 is also divisible by 6. So the answer is 0. So this is also one pair. And lastly, if you see the 6 and the 12, and if you add both the numbers, 6 plus 12, it will be 18, and 18 modulus 6 will also give the result as 0. So the total answer will be 3. But if you keep on trying all pairs, so our time complexity will be O of n square, right? Because this is a kind of a brute force app. So let's see how we can optimize this further. So let's look at the maths of it. So you have been given that a of I plus a of j whole mod m should be equal to 0. And you have to find such ij pairs. And the only condition is the I should not be equal to j. So if you express that same expression which you have got here with the modulo operator, you can express it as a of I mod m plus a of j mod m and whole mod m. So if you just look at this number, so what is the range of this number? It will be in the range of 0 to m minus 1. Similarly, for this number also, the range will be 0 to m minus 1. And if you add both these equations, so your total range for this expression will be 0 to m minus 1 plus m minus 1, which is equal to 2m minus 2, right? So how many multiples of m will be present in the range of 0 to 2m minus 2? It will be 0 and m only, because you cannot take 2m, because it will overflow from the boundary, since our range is till 2m minus 2 only. So we have exactly two multiples, one is 0 and another one is m. So now our this problem statement will come down to a of I plus a of j should be equal to 0, one problem statement, and the next will be a of I plus a of j should be equal to m. And this we can express as a of j is equal to m minus a of I. So I have seen that how this problem is broken down into two simple approaches. So let's see the code for this. So you have defined a function pair sum divisible by m. You have taken the array as a and modulo constant as m. Now you have taken one hash map. This, don't worry about this, we will learn in the next class as well. So hash map is something where you can keep key value pair. So now you will run a loop from for I is equal to 0 to n minus 1, and you will calculate the value. And your value, if your value comes as 0, anything added with 0, if the answer is also 0, then this number should also be 0 only. So if the value is there 0, then its pair is also should be 0. So one of the pair is 0. Similarly, if the value is not coming 0, then the other pair would be m minus value, right? And just we will count the frequency of that pair in an answer variable, and we will increase the frequency of the value in our map. So let's understand this code with this example array and with this dry run. So first of all, our control will come to here. For the first element, 4 modulo 6 will give the value as 4, right? So what will be the pair? So since value is not equal to 0, this will come to this block, right? So the pair will be 6 minus 4, which is equal to 2. And in the answer, we will count the frequency of that. So do we have any pair of 2? No, right? Till now in the frequency map, we don't have anything. So in the answer, we will add only 0. Now, since we have already evaluated this number, we will keep its frequency that it appeared one time. So we have kept that value in our frequency map and updated the count as 1. Now let's move on to the second element. So 3 mod 6 will give the result as 3. The pair will be 3. Since 3 is also not present right now in our frequency map, so the answer will be still added with 0, and in the frequency map will be updated with 3 as 1 because 3 appeared one time. Next we will move to the 6. 6 mod 6 will be equal to 0. So we will come here, right? So our pair will be 0. Now we will check if we have any 0 pair already present in the array or not. Since 0 is not present, so the answer will be again added with 0 only, and the frequency map will be updated with the 0 value with its count 1. Similarly, for the next element 3, the value will be 3 mod 6 will be equal to 3 only. The pair will be 6 minus 3, again 3, but this time 3 is already present, right? So we will increase the answer with 1, and we will increase the frequency of the 3 because 3 was already present with 1 count. Now it will be 2. Next we will move to 8. 8 modulo 6 will be 2. Again we will come to this block. Now pair will be 6 minus 2, which is 4. Since 4 is already present, so our frequency map will get updated, and the answer will also add 1 into it. So after this, the answer was 1. Now this answer is 2, and the frequency map for the fourth key will also increase from 1 to 2. And similarly, for the last element, 12 mod 6 will give the result as 0. This will come in this block, and it will see that 0 is already present in the array. So it will again add 1 to the answer. Now the answer will be 3. And since 0 was already present in the array, so frequency of 0 will increase to 2. So now you have seen that how we have mapped this dry run in with our code. So this is a lead code problem. The link I have mentioned in the description. And also you can see that since we are running one for loop, which is from for I is equal to 0 to n minus 1, so our time complexity is O of n, and we are taking one extra hash map, so our space complexity will be O of m. So now let's understand what are GCD and how we can use this GCD. So what is a GCD? GCD means greatest common divisor. So what is the greatest common divisor? Suppose A is a number which is completely divisible by x, and B is a number which is also divisible by x, and x is the maximum possible integer, then x can be considered as a GCD. So let's see that with an example. So what is the GCD of 15, 25? So let's first understand what are the divisors of 25. So divisors of 25 are 1, 5 and 25, right? Similarly, what are the divisors of 15? So when I say divisors and factors are same. So what are the factors or divisors of 15? 1, 3, 5 and 15. So in both these two numbers, which is the greatest number which is dividing both of them? It is 5, right? So 5 is the greatest number which is dividing both 25 and 50. So 5 will be considered as the GCD of 15, 25. Similarly, for this GCD of 12 and 30 also, we can easily see what are the factors of 30? 1, 2, 3, 5, 6, 10, 15 and 30. Similarly, what are the factors of 12? 1, 2, 3, 4, 6 and 12, right? If you see, what is the greatest number which is dividing both of them? This is 6, right? So GCD of 12 and 30 will be 6. So there are some edge cases as well. So what if GCD of 0 along with some number is given? So that time the answer will be the number itself only. And what if there is a prime number given with one of the non-prime number in the GCD? In that case, the GCD will be 1 only. So let's see some properties of GCD. So first property is GCD of A comma B will be equal to GCD of B comma A. Similarly, just now we have learned that when we do GCD of any number with 0, we will get the same number. Similarly, if we have to calculate GCD of some n numbers, then it can be calculated in any order. So GCD of A comma B comma C can be calculated as GCD of A comma GCD of B comma C, or it can be calculated by GCD of B comma GCD of A comma C, or in any other combination. So the order really doesn't matter anymore. So let's see one more interesting property of GCD. So GCD of A comma B is equal to GCD of A minus B comma B. So how we are getting this? So you can memorize this as well, but it is optional for you. We will see in the last that how we are able to get GCD of A comma B as equal to GCD of A minus B comma B. And using this property, we can get one more property. So suppose GCD of A comma B, we already know that GCD of A minus B comma B. So if you again subtract this term, you will again get A minus B comma B. Similarly, if you again subtract, it will be A minus B minus B comma B. So we already learned from our modulo class that any number of times we can do subtraction that can result a modulo. So GCD of A comma B will be equal to GCD of A modulus B comma B, considering the fact that A should be greater than B. So this number should be greater than this number. So in this way, it is like a shortcut that every time you don't have to count factors, you just do the subtraction and you will get the GCD of it. So let's see that with an example, the GCD of 20, 6. So let's consider is that A and B. So A minus B done one time, it will be GCD of 14, 6. Again, we are subtracting 6. GCD of 14 minus 6 will be 8. It will be GCD of 8, 6. Again, we can subtract 6. It will be 2. Now we cannot subtract it. So GCD of 6, 2 will be 2 only, right? And also, if you express it via counting number of factors, there also you will get that 2 is exactly 20 mod C also. So this algorithm jumps straight to the remainder, skipping all the loop. So this technique is called Euclidean shrinkage. So on this extension, so there is Euclidean algorithm also present. How to write the code for the GCD? If A is lesser than B, using the property GCD of A comma B is equal to GCD of B comma A, we can simply return that GCD of B comma A, so that the first number becomes bigger. Because if the first number becomes bigger, then only we can use this formula, that GCD of A comma B is equal to GCD of A mod B comma B. If B is 0, again, this is the GCD property that we have to return the other number. Similarly, if both this condition is not true, then we will simply do GCD of B comma A mod B, or it can be expressed as GCD of A mod B comma B. But if these two conditions are false, that means B is greater, right? B is greater than A. In that case, the first number will be B and the second number will be A modulus. So what is the time complexity? So the time complexity of this will be O of log of max of A comma B. So if 112, you have to calculate GCD of this. What is the max of these two? It will be 100. So it will be O of log of 100. The result will be like this. We will not go into deep that how we have calculated the time complex. This is something which you can remember. This is beyond the scope of this video as well. So let's see how to find the GCD of an array. So suppose you have been given an array A 15, 30, 12. So you will simply run a loop from I is equal to 1 to n minus 1, and you can simply calculate the GCD using answer is equal to GCD of answer comma A of I. Since answer has been initialized with A of 0, so it will be like GCD of A comma B comma C can be expressed as GCD of A comma B and whole GCD of C. Like that, we can calculate GCD of a complete array. So what is the time complexity? Since we are running a loop from I is equal to 1 to n minus 1, so that's why O of n into how we are calculating the time complexity of GCD of two numbers, we simply have to keep that formula, but instead of max of A comma B, we will keep the complete array, like max of A of I. So let's see that optional proof which I was talking about, that how we get that GCD of A comma B is equal to GCD of A minus B comma B. So let's assume GCD of A comma B is equal to D. So what does this mean? So if we go through the definition of GCD, so GCD of A comma B if is equal to D, then that means that A mod D is equal to 0 and B mod D is also equal to 0. So if we simply subtract these two expressions, we will get A minus B modulus D is also 0, right? So from these three, what we can conclude? That D is a factor of A comma B as well as A minus B. Now let's see the second expression. So let's write that GCD of A minus B comma B is equal to T. So what does that mean? That means using the definition of GCD that A minus B mod T will be equal to 0 and the second number which is B mod T is also equal to 0. So if you simply add these two expressions, you will get A modulus T is also equal to 0. That means T is a factor of A, B and A minus B. And here, if you closely observe from the second expression, that T is a common factor of A and B. And from the first result, we have concluded that D is a greatest common factor. So T must be lesser than or equal to T. From this we can conclude, right? But if we think in other direction as well, that D is a common factor of A minus B as well, and D is the common factor of B as well, right? And from this expression, we have understood that T has become a GCD, a greatest common factor of A minus B and B, both, right? using this one. So this 2 is linked with this one, and this one is linked with this 2. So if you see, we got two expressions. T is lesser than equal to D and D is lesser than equal to T. So from this two expression, we can conclude that this two expression can only hold true if T is equal to D. So from this, we have proved that GCD of A comma B is equal to GCD of A minus B comma B. It is totally okay for you to skip this as well if you have not understood. Just for the sake of understanding the mathematics behind the GCD property, I have come up to this proof. So you can skip this. So to summarize, today was all about total mathematical control. We learned that Modulo protects our variables by writing infinite growth around a strict boundary. We also saw how GCD accelerates your loops by geometrically shrinking boundaries via remainder math, right? In our next lecture, we will be diving into the basics of hashing. If you found this breakdown helpful, hit that like button and subscribe to Techmine Guru. Till we meet again, keep coding, keep optimizing, and keep learning.